Hello everyone, my name is Hooman. The title of my talk today is Profiling Exciton Generation Rate in Conventional and Inverted Bulk Introduction Organic Solar Cells. But before talking about my research, I would like to talk about a very serious problem in the world, which is called global warming. Global warming is the rise in the average temperature of climate's Earth system. Without a decisive action, global warming will culminate in a significant climate degradation. Nevertheless, different ways to mitigate this serious problem, replacing fossil fuels like oil and gas by renewable sources of energy like solar energy and wind energy is the most practical way. Also, among different types of renewable sources of energy, solar energy is the most accessible and reliable. And also solar energy is the only energy that is coming from out of our planet. Therefore, it's free energy because we do not need to use our sources of energy on our planet. One of the best ways of using solar energy is solar panels, which consists of solar cells. These days, you can see heavy and expensive solar panels on the roof of the buildings. But what if we could install solar panels on our clothes or on our tent or on our bag and produce electricity and charge our phone or turn on the television or light and simultaneously mitigate global warming? And what if these types of solar cells were very cheap and everybody could afford it? Yes, we can do it in close future by organic solar cells, which are thin, light, flexible, and cheap solar cells. However, the efficiency of organic solar cells is low yet, and in order to commercialize them, we need to increase their efficiency. But for increasing the efficiency, first we should clearly understand how an organic solar cell works. The operation of organic solar cells consists of four processes. First, absorption, diffusion, dissociation, and charge collection. Upon absorption of a photon or solar radiation in the active layer of an organic solar cell, an electron is excited from HOMO or highest occupied molecular orbital to the higher energy level or LOMO or lowest unoccupied molecular orbital. Instantly after that, this electron hole gets bound to exciton, but formation of an exciton in an organic solar cell is not favorable because in order to produce electricity, one needs free charge carriers. Therefore, this exciton should be dissociated into free charge carriers. Dissociation in an organic solar cell takes place at the interface, therefore this exciton should diffuse to the interface. After diffusion of exciton to the interface, because this electron is located at a higher energy level than that of acceptor's LOMO, it gets transferred to the acceptor's LOMO. But I should create a charge transfer or CT exciton. But I should mention that this CT exciton is not dissociated yet, because for dissociation it requires an external energy at least equal to the binding energy. This external energy comes from the excess vibrational energy due to the formation of CT exciton. If this energy is adequate, it may impact back to the CT exciton and leads to dissociation. After dissociation, these free charge carriers are collected by the respective electrodes and electricity is generated. However, I should mention that there are some traps in the organic solar cell material because of defects, and sometimes some of these free charge carriers are captured by these traps, and therefore it will lead to the lower efficiency. This figure is showing the schematic structure of a conventional organic solar cell. In conventional organic solar cell, the anode is deposited on the glass, therefore after creation of holes and electrons, holes are traveling to the top. But another instruction is inverted structure. In inverted structure, the charge collection is opposite, therefore on the glass, the cathode is deposited, and therefore after creation of holes and electrons are traveling to the top. In order to compare these two structures, we have simulated organic solar cells by solving the mathematical equations those govern the physics of organic solar cells. And the simulation results have shown that the efficiency of inverted structure is about 13% higher than the conventional structure. In order to investigate the reason of this increment in efficiency in the inverted structure, we have plotted the exciton generation rate as a function of position x in the active layer for three different active layer thicknesses, 70, 150, and 250 nanometers. And we have calculated the areas under these curves which are showing the total exciton generation rate or total absorption. The results have shown that the total absorption of inverted structure is higher than conventional structure, and this is the reason for higher efficiency in inverted structure. In order to compare these structures more profoundly, we have plotted also normalized modulus squared of electric field, which is showing the absorption as a function of wavelength of light and position x in the active layer for 3 active layer thicknesses, 70, 150, and 250 nanometers for both conventional and inverted structures. The results have shown that at the end of the active layer of inverted structure, the absorption is higher for whole wavelengths and thicknesses for inverted structure. This can be attributed to the better reflectance of the whole transport layer, MO3, in the inverted structure, which does not exist in the conventional structure. Also, in order to investigate the position of pickup absorption in the inverted structure, we have plotted normalized modulus squared of electric field as a function of position x and wavelength for 3 different active layer thicknesses, 70, 150, and 250 nanometers as contours. And the results have shown that for 70 nanometers, the peak is located almost at the middle, and this means that most of electrons and holes have to travel almost the same thickness to reach the respective electrodes. However, for 150 nanometers, the peak is located on the right-hand side, and this means that electrons have to travel a longer distance to reach the cathode. And on their way, they may be captured by the traps, and this may lead to lower efficiency. For higher thicknesses, for example, 250 nanometers, this peak of absorption is split to 2 parts, and therefore, for most of electrons that are located on the right-hand side, have to travel a long distance to reach the respective electrode, and most of the holes have to travel to most of the holes that are located on the left-hand side have to travel a longer distance to reach the anode. And on their way, they may be captured by traps again, and this may lead to lower efficiency. To wrap up, simulation has shown that the inverted structure has higher efficiency than that of a conventional structure, and it is shown that the increment of efficiency is due to the higher absorption in inverted structure, and the position of peak of absorption have been investigated for inverted structure. References, and thank you for your attention. Yeah.
Okay, I think I might kick off with a question again. Now, what's the application, the main application that will be used? I mean, what will be your main sort of target, to swap, a conventional photovoltaic cell for that model that you are?
Inverted structure?
Yes.
Okay, but as I mentioned, the organic solar cells are not in the market yet. They will be in the market in the future because of some problems like efficiency. Actually, inverted structure only swapping the anode and cathode. Mm-hmm. This actually lead to higher efficiency. And our objective was to increase the efficiency, and the simulation has shown that if we use inverted structure, we will get actually higher efficiency. Yeah, and the application.
Yeah, I mean, how the acceptance of this product, and once we have the right efficiency, it will become more competitive to a photovoltaic cell.
Oh yeah, okay, but I think that in comparison to silicon solar cells, which are the first generation, you can see on the buildings, on the roof of the buildings. This is third generation, and it's very cheap. I think that is the most important part. It's very cheap, and it's light, flexible, and you can install, for example, on your clothes. Yeah. If I get to your question.
Yeah. Actually, I've got another interesting curiosity more so.
Yeah, sure.
What's the life expectancy of that, to maintain?
Yeah. Okay. Yeah. Good question, actually. And one of another problem of these types of solar cell is lifespan, as we said.
Yeah.
Now maybe some months these days, maybe some months or even 1 year, not more than that. But another objective of actually people in the universities who are working on this is to increase the actual stability. Yeah. But one of the problem is stability of these types of solar cells. Yes.
Okay.
Yeah.
Thank you.
Do you put any validation work into your model? Like, how do you make sure you're getting the right results?
Yeah. Okay. We compared with some experimental works. Yeah. This is one of them is for conventional and simulation, and one of them is for conventional and measured by in the lab, and again 2 for inverted structures. And we compare with the experimental works, and yeah, we validate it by experiment.
Well, let's thank Hooman for your
No
wonderful
worries.
presentation.
Thank you so much.